Hello, this is Daewon Lo from KAIT, South Korea. My presentation title is Design and Analysis of HDMI 2.1 connector for crosstalk reduction using taps and immerse taps. This is contents. The first chapter introduces the evolution of HDMI and explains many of the signal integrity issues that occur in connectors. The second chapter discusses crosstalk reduction design analysis through capacitance variation in plug and receptacle. In the third chapter, the performance of the proposed design is verified by comparing it with the existing design and the design that simply reduces capacitance. Finally, we would like to conclude with a conclusion. This is the evolution of high-definition multimedia interface, HDMI. HDMI is an interface that can transmit video, audio, and control signals at once. With the development of displays, most TVs support 4K and many 8K displays have begun to be produced. In doing so, bandwidth increases. In 2002, HDMI 1.1 development began, and at that time it had a bandwidth of 4.95 GBps. And it gradually increased from version 1.2 to 10.2 Gbps, from version 2.0 to 18 Gbps, and from version 2.1 to 48 Gbps. With this increase of bandwidth, the speed also reached 12 Gbps per channel. But the high data rate causes various signal integrity problems. These signal integrity problems do not occur with well-shielded cables, but rather with connectors with high impedance discontinuity and crosstalk, as shown in figure here, as the plug and receptacle are combined. Signals enter, and these signals are greatly degraded by signal integrity issues, such as impedance discontinuity, crosstalk, and channel losses. Among these degradation factors, as the speed increases, the influence of crosstalk becomes even greater. Therefore, in order to solve the signal integrity problem, it is important to design the HDMI connector considering the signal integrity. Previous attempts have been made to improve the signal integrity of these HDMI 2.1 connectors. In the low left figure here, A is the original shape and B is the proposed modified shape in that paper. These changes improve signal integrity. However, the insertion loss and HDR were improved, but the TDR impedance was rather bad. In addition, this improvement of signal integrity is a simple change by reducing the length of the line, and the effect of changing the shape of the pin is very low. Therefore, it is necessary to design a pin that can improve both loss, HDR, and TDR impedances. So far, we have briefly explained why signal integrity is important in HDMI connectors and introduced previous research on this. Afterward, we analyzed the effect of each capacitance through capacitance variation of a plug and receptacle in HDMI 2.1 connector. In the next chapter, we will talk about the contents designed with these effects in mind. First, the setting to simulate the capacitance change are as follows. Each channel has differential line and a ground line is added between the differential lines. Since the crosstalk of D1 and D0 channel, which are located in the middle of the differential lines, was the worst among them, D0 was selected as the target line, and analysis was carried out. And the D1 and CK lines next to it were simulated by simply putting capacitance with one single line without putting all the differential lines. The capacitance in the plug direction and the receptacle direction is designated respectively, and the names are as follows. The capacitance between the differential channel and the ground is set to C self. The capacitance between the lines of the differential channel is set to CM1, and the capacitance to the nearest differential line is set to CM2. This is the simulation result by changing the capacitance of the plug side. ACL is compared. First, ACL is an attenuation to crosstalk ratio, and it can be considered as a number indicating how large the crosstalk is compared to the insertion loss. At this time, there is no difference in ACL by changing the self-capacitance and the M1 capacitance. Since the signal and ground are already separated on the plug side of the pin, even if C self and CM1 increases, crosstalk is not affected. On the other hand, decreasing the M2 capacitance will decrease the ACL, but the distance between the differential lines in the plug is already far enough that it cannot be improved. Therefore, crosstalk improvement in the receptacle is essential. This is simulation result by changing the capacitance of the receptacle side. Unlike plugs, any change in capacitance affects the ACL. The increase of self-capacitance and M1 capacitance lowers the ACL of about 1 GHz to 6 GHz band. Also, when M2 capacitance becomes smaller, ACL decreases in all frequency bands. Therefore, it is necessary to increase self-capacitance and M1 capacitance and lower M2 capacitance in receptacle to improve ACL. In this chapter, based on the analysis of the capacitance change in the receptacle, we designed the pin shape of the connector and we will use it through simulation. As previously analyzed, since crosstalk cannot be reduced in plug, crosstalk must be reduced by changing the receptacle. In general, changing the channel width and thickness to the reduced vector. In this case, C self, CM1 and CM2 increase and decrease at the same time, so the vector does not improve significantly. Also, reducing capacitance to reduce vector causes impedance increasing. Therefore, it is necessary to design the channel so that the vector decrease and improve control using taps and inverse taps. Inverse taps is a method of subtracting the taps from a line. Unlike the method of attaching taps to a line, also the default and ideal one and the proper design are shown here. To reduce vector, ideal one only reduce CM2 using inverse taps. Inverse taps are subtracted on differential signal lines. We propose the design as reducing M2 capacitance to the nearest differential channel using I taps, and increasing self-capacitance and M1 capacitance using taps. Taps are added on ground lines. The TDR impedance is lowered by increasing the capacitance using taps. All designs were simulated and compared using 3D electrical magnetic simulations. We compared the TDR impedance, ACL, and differential line insertion loss. The dotted line in the ACL and insertion loss graph is the HDMI 2.1 spec. As for TDR impedance, CK and D2 lines are the worst case, so the D2 line is set as a target. The rising time of TDR is set to 75 picosecond. From the TDR impedance result, it is a receptacle from 1 to 0.2 nanosecond, and a plug from 1 to 2 to 1 to 4 nanosecond. The plug has no design change, and thus the TDR impedance is the same. ID1 decreases CM2, which increases the impedance. In contrast, the proposed method decreases the impedance by increasing C self and CM1. Also, CM2 is reduced. It has been proven that the proper design improves the TDR impedance. This is comparison of HL. As shown here, the default is better for about 5 GHz to 7 GHz, but the proper design is better for all except this band. Compared with ideal one is better for 0 to 3 GHz, but the proper design is better for 3 GHz or more. It has been proven that the proper design improves the ACL. This is comparison of insertion loss. The proposed design is better than the default design and ideal 1 design in the entire frequency band. Like ideal 1, ITAPS lowers the capacitance between signals and improves losses. As in the proposed design, adding a tap to the ground line increases the capacitance between the signal and ground, resulting in low capacitance between signals and better impedance matching. Loss is further improved. It has been proven that the proposed design improves the insertion loss. Finally, the proposed design improves all three of TDR impedance, ACL, and insertion loss compared to the default design. This is conclusion. In this paper, we propose and analyze the design to crosstalk reduction using taps and I-taps. The effect of each capacitance was analyzed through a capacitance case study. Inverse taps were used to lower backs, and taps were used to further improve backs and lower impedance. The proposed design using taps and I-taps achieved all improvements in crosstalk, impedance, and insertion loss compared to the default design. Yeah, thank you for your attention and feel free to ask a question. And if you would like to discuss something, please contact us at the email address below. Thank you.